binary tree is a tree which will going to have a nodes as well as edges or a branches that will be connected to each other. It can have a 0 node or maximum of 2 children for each node. We have a node that consists of left subtree and right subtree, and in order to make use of its memory address, we require L-link and R-link respectively. If the position of a binary tree index is 0, that is considered as a root node. If the index is I is 0, then it gives the position of a root node. Hello everybody, a warm welcome to one and all. Welcome to the last session, last chapter and last unit of your B.Ca second semester, subject called Data Structures using C. I am Rohini TS, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. So in our today's session, we are discussing regarding this binary tree. As we all know that in the previous session of this chapter, we had a discussion regarding what do you mean by binary tree, and also I have discussed regarding the different types of binary tree. So in this we got to know the definition of a binary tree, and also have discussed what are the different types of binary tree we have. So in our today's session, we are going to learn about how we are going to represent this binary tree with respect to array, and also I will be discussing what are the operations can be done on this binary tree, and also at last we will see what are the different way of traversing a binary tree. First, we will see the array representation of a binary tree. Already you know what you mean by an array, right? An array will going to have a collection of homogeneous element. It will going to store a same data type of element, and we are using this array, that is linear data structure. Memory will be contiguous in order, sequential order, memory allocation will be there. By making use of that, we are representing this binary tree. Binary tree is a tree which will going to have a nodes as well as edges or a branches that will be connected to each other. It can have a 0 node or maximum of 2 children for each node. The trees can be represented using sequential allocation technique. If it is sequential, then I can say that as a arrays, or by allocating the memory for a node dynamically. So I am allocating a memory space and we are representing it with the help of this linked allocation technique. We have a two kinds of methodology in order to represent a binary tree. One is arrays, and by making use of a linked list here. So we will see about the first type, that is what? Allocation of a memory space by making use of this linked allocation technique. So in the linked allocation technique, a node in a tree has a 3 fields. So if you consider a linked list also, it will comprises of a 3 parts, right? What it comprises of? It will going to have a L link, and it has a info, and it will going to have R link, right? And also you can say we have a node that consists of left subtree and right subtree, and in order to make use of its memory address, we require L link and R link respectively. So here we have a info, L link and R link. Already know about it, right? Info will going to have a actual information, and L link will going to hold the address of left subtree, and R link hold the address of right subtree. Then how we are going to create a node? Already you know to create a node in a linked list. In the same way, I am creating a node for this binary tree, but I need to have a 2 link. If you consider the linked list, it will going to have only one link, which is of the link of a next node. But when we have this binary tree, in this we have a 2 subtree, one is left and right. So for that I need to have a 2 link. How we are going to create that? By making use of a structure to hold a different data types. Struct node, and we have a int info. I am creating a variable called info, which is of a data type integer, and struct node L link. Here we have a pointer variable that will going to hold the address of the link node, and struct node star R link, that is pointer variable R link. It will going to hold the address of this right subtree, and I can have any number of nodes for it. Type def struct node, and we have a main node. That means we are creating a alias name here, that is type definition we are giving to the node as this capital NODE. And next here you can see that a pointer variable root can be used to point to the root node. And 3 pointer variable we have root, r-link, l-link. Root is used to point to the root node, and if the tree is empty, then the pointer root will going to be null. If there is no node, or if it is not pointing to any of a node in a binary tree, then that root will going to be assigned to null. So if the root is equal to null, then we don't have any element in the binary tree. If the root is null, then we can say that that binary tree is empty. Then the pointer root can be declared and initialized. How we are going to declare the root node? Node, we have a data type, and root is a name, that is initialized to null. So if root is equal to null, then that time this tree is empty. And we can use this get node and free node in order to allocate and deallocate the memory space dynamically. Get node and free node function we have. With the help of these two functions, we can allocate the memory space. That is all regarding what representation by making use of a linked list technique. So next what we have here, that is sequential allocation technique. So here with the help of this arrays concept, that is what collection or ordered collection of homogeneous element, we are representing the binary tree. How we are doing? A tree can also be represented by making use of this array, and we are calling that kind of allocation or representation of a memory as a sequential allocation technique. So here you can see that here we have a binary tree and it has a certain number of nodes. This is considered as a root node, and we had given a numbering 0, 1, 2, 3, 4, 5, 6. This is what in order. In order to represent this in the array, I must know its index. So root node index is 0, and next I have a 1 that will comes to the next place. Then how we are going to represent it? In this manner, A, B, C, D, then I can have E, F, G. So then this E will going to be stored in 4 and F will going to be stored in the 5th location, G will be in the 6th location. This is what the sequential representation of a tree. So in order to represent this in a sequential representation node, here first you need to understand certain key points with respect to this. So we are going to numbering that different nodes of a binary tree sequentially 0, 1, 2 up to last leaf node. So if it is 0, then that position is considered as a root node. If the position of a binary tree index is 0, that is considered as a root node. If the index is I is 0, then it gives the position of a root node. I is a iteration. If it is equal to 0, then that is the link or address of a root node, and the given position of any other node is I is 2i plus 1, that will give the position of the left child, and 2i plus 2 will going to give the position of right child. If I wanted to know its address, or if you wanted to represent its memory allocation, you must know the address. I if is equal to 0, that is a root node. If it is 2i plus 1, that gives the address of left node, and if it is 2i plus 2, then that will gives the address of this right child node. So if I is the position of the left child, then this I plus 1 is going to give the position of the right child. If I is the position of the right child, then I minus 1 gives the position of the left child. This is just what mirror image things. So in this, given the position of any node I, the parent position is given by I minus 1 divided by 2. So if I is odd, then it will going to points to the right child. So this is what the numbering we are going to give in order to find out which is left node and which is right node as well as root node. So here we have a different ways in order to represent this node by making use of a sequential allocation technique. In that, first we are going to use some of the location may be used and some may not be used. So if you consider the binary tree, in that some location may be used or may not be used. So for this we are going to use a flag. So flag field, we are calling that flag name as a used. So here used is the name of a flag. So I have a flag in order to indicate which node is using a memory, which node is not using a memory. So we are using a flag called used. That used is used just to indicate whether memory location is used to represent a node or not. So if the flag field is used is 0, then corresponding memory location is not used. So if the used value or if the used flag value is 0, then we can say that memory is not used. And if it is greater than or if it indicates the absence of a node at that position, if this flag value is any other value or if the used value is non-zero, then we can say that memory got utilized. And here each node contains the two field, one is info and another one is used. So info is used to specifies the actual information what is storing in that particular root node or any node, and used is used to indicate the presence or absence of a node. So if the used is 0, then there is no element, that is absence of a node. If used is non-zero, then we can say that it is presenting or it is representing a node. And also you can see the structure declaration for this. Define max size 100. I am giving a size of a binary tree as maximum as 100. Then struct node and int info, int used. I am creating two variables. One is info, one is used. So as I told earlier, used can store 0 or non-zero value. So I require integer. I have these two field in the node and I am closing this structure here and type def struct node. An array of type node can be used to store the different item, and the declaration for this, we are going to have a node a max size. So here you can give the size of a array, that is maximum size of an array. So if you are giving that number of memory will going to be allocated. And we have a second technique. Other than using this flag called use, we have one more technology here. Instead of using a separate flag field use in order to check whether the presence of a node or absence of a node, we can initialize each location in the array to 0. So instead of having a flag used, we are initializing all the node location as a 0, indicating the node is not used. So if it is in the format of 0 itself, then we can say that it is not used. So if it is turned to any other value, then we can say that memory allocation or that node has used the memory allocation. So here non-zero value in the location indicates the presence of a node. So in the previous technique, we are going to use a field called used. So this used is going to represent whether memory is taken by the node, whether node is present or absent. So if the node is absent, then it indicates the 0. If it is present, then it will going to use non-zero. But in the second technology, instead of using this separate flag called use, I am going to initialize all the memory space, or we are going to initialize all the location in the array to 0. If it is array till the operation completion, then I can say that there is an absence of a node. If it is converting to non-zero value in the location, then we can say that there is a presence of a node in that particular memory allocation. So these are the different techniques we can have in order to have a sequential allocation technique. Next, we will see the operations which can be performed on a binary tree. We can have a insertion, traversal, search, copying, and then deletion. When it comes to insertion, we are insert a given item into a tree, and traversing in the sense what? Visiting the nodes of a tree one by one. So we are traversing from the first node to last node and searching for the specified item in a tree, whether it can be left subtree, right subtree, or a root. So we are just searching the item or a particular item and copying to obtain the exact copy of a given tree. I am having a replica of a tree, then I can say that as copying, and deletion to delete a node from the tree. So these are the different operations which we can perform on a binary tree. We'll see the last topic, that is regarding traversal of a binary tree. As of now, we got to know that traversing in the sense what? Visiting each node exactly once or one by one from the beginning to end, moving through all the nodes of a binary tree or visiting each one at a time. That is what we are calling as a traversing. And how do we traverse? It's always based on the type of application. Based on the type of application that indicates how we are traversing. So here You can see that if I am doing a traversing, then I can indicate that with the help of V. Then traversing the left subtree, then we require L. If I am traversing a right subtree, then it is of R. Then we have a different 6 ways in order to arrange them. How do we traverse? How can I visit? Whether should I visit the left node first, or a left subtree, then root, then right subtree, or right subtree, root, then left subtree, or left subtree, root, right subtree. We have a different techniques in that VLR, that what root, left, right, then left, root, right, then we have a left, root, left, right, root, then we have a root, right, left, then we have a right, root, left, then right, left, root. We have a different ways in order to arrange them. Out of this, we are going to give only the importance for standard convention, that is of 3 types, that is VLR. What it means? First I need to visit a root node, then left, then right subtree. Here first left subtree, then root node, then right subtree, then left, right, then root node. So we are calling it as a pre-order, in order and post order. So you need to concentrate on the V. So here if V is at first, that is pre-order. If V is in between, in order. If V is at the last, then that is post order. So first I will visit the root node, then left, right. So here first I visit the left subtree, then root node, then right. Then here in the post order, first I visit the left subtree, right subtree, then I will go to the root node at last. So based on this, we are going to have a traversing. We'll see each type. First we have a pre-order traversal. If I say pre-order, then we have a V, that is first I need to visit the root node, then traverse the left subtree. If it is left subtree, L, then we have to traverse the right subtree, then that is R. So in this manner, we are going to visit, or we are traveling in the pre-order traversal. If you consider this example, I have a 3 node 1, 2, 3. Fine. Let me consider the value as 10, 20, 30. So when it comes to the pre-order, pre in the sense I need to visit the root node first. That is what? V, then this L, then R, or a right subtree. Then how it will be? 10, 20 and 30. Fine. This is how we are traversing in the pre-order traversal. So in this pre-order traversal, root is labeled as 1, and which we are going to visit first. Then we have to move to the left subtree. Then the left subtree contain only 1 node, that is considered as 2, and it is visited the second. In the pre-order traversal, we move to the right subtree at last, that is labeled as 3. What is the order then? 1, 2, 3, that is 10, 20, 30. In the same way, we have a in order. If it is in, then we have a V in between the left subtree and right subtree. So it can be recursively defined as traverse the left subtree in order. First, I need to traverse the left subtree first, then process the root node. So if it is root node V, then we have to traverse the right subtree, L, V, R. Then how will be the allocation here? Let me consider 10, 20, 30 again. Left subtree, first I will visit the node 20 and I will come to the root node, that is 10, and I will come to the right subtree, that is 30, 20, 10, 30. Here also you can see the order 2, 1, 3. That is regarding in order traversal. What about post order then? As the name indicate, post in the sense at last. First I need to traverse the left subtree, then I will visit the right subtree, then at last I will visit the root node. Then L, R, V. So if you consider this, you can see first I will visit this left subtree. Let me consider 10, 20 and 30 again. So here 10, 20, 30, first I need to visit the left subtree, that is 20, then I will visit this right subtree, that is 30, and at last I will visit the root node 10, 20, 30, 10. Then how will be the order? 2, 3, 1. This is how we are going to traverse in the post order traversing. I hope you all enjoyed my today's session, and I am done with the data structures using C. Let me meet you in the next session with further more subjects. Until that, keep learning, keep on growing. All the very best for your examination. Thank you.